Alrighty folks, welcome to Module 2 for Computer Graphics. Let's go ahead and dive into it. Let's see what's in store for this week. So, just taking you to the web page, a reminder that today your lab will be due anywhere on Earth for Lab 1, so make sure that is in your GitHub repository. If you're just joining us for the class, make sure that you click on the course monorepo link here relatively soon so that you can get the resources required for the course. And for today, we're going to jump into Module 2. And don't forget to do the in-class activity, as always, within a week of this module opening. Okay, let's take a look at Module number 2 here. Okay, so as always, I'd like to start with a little pre-class warm-up. And as we're getting started with things this semester, one thing to keep in mind, just resources to get you excited about C++, graphics programming, and related topics. CPPCon, it's a great conference, if not the largest conference in the world on C++, but they've got a lot of really fascinating talks on just game programming, graphics programming, and C++ in general. And those range from advanced topics, if you're really into sort of C++ and learning some stuff, or beginners. There's a Back to Basics track, which I've presented at before, and you can see some of these tutorials here. They're really quick, you can play them at 2x speed and learn some interesting things about how to design software. So I'll pick out a few probably during the semester that I think are good, and you'll see them pop up. But otherwise, just want to make this another resource available to, again, get you excited and immersed in this topic here. And with that, I also want to introduce to you another pioneer of computer graphics. This is Michael Abrash. He is an engineer right now at Oculus, and he's worked on several games, Doom, Quake, that sort of series of first-person shooter games. And these are really two of the games that really defined 3D real-time graphics back in the day. In the topic particularly that we're going to talk about today on software rasterization. So he wrote this excellent book. It's actually still super relevant today, this book, because the principles that have been applied or written about here are fairly timeless. The languages and stuff update a little bit. This book's in C, but it's really a nice resource. In fact, I want to just Google this really quick, and I'll add a link to it because it is free. And most of the time, I am able to find the single page to it here. So I'll just go ahead and do that. And it was released online here, and I believe there is a HTML single page that you can generate here. So let me go ahead and just link this here so that you have it available. Here you go. So here's all of these sort of chapters. Some of these things aren't going to be as relevant, such as reading about the old processors, but the content as far as what he's writing about and looking at is still good. So you might see some things that are going to be relevant, like there's a chapter today on Bresenham's algorithm here, which is all about line drawing. So I think this could be, a nice backup resource here. So I'm just going to go ahead and, feel free to use this or cite this, but I'll go ahead and link it here. Link to book here. Okay, so with that said, that's Michael Abrash, and he's really worked on a lot of interesting projects again, so it's just somebody to know about, and hopefully his book can be useful. Okay, so we're obviously recording here, so we'll continue along here. Again, the logistics lab 2 is out. It'll be pushed to your repos, so just do a git pull from your directory. So that is just navigate to wherever your mono repo is, for example, and just type in git pull, and that'll bring in a new directory with with lab 2. Assignment 2 will be released early next week, so that means you still have a few more days to work on your assignment 1, okay, A1. And last time we talked about sort of your introduction to the course, some of the topics. Here you got familiar with the website, syllabus, structure, and so on. And then we talked a little bit about graphics domains, OpenGL a little bit, and did a little bit of just introduction to C++. So we're going to continue that today, talking about C++ and some various graphics topics. And today's topic of the day is software rendering. So as I mentioned last time, we're going to start by building a software renderer. Before we can jump into all of the hardware stuff, this is a great way to get introduced to the math, how graphics works in general. Okay, so building a software rasterizer. So if you will, I'm going to take you back to the 90s when software rasterizers were the norm. Here's some 90s things that I remember from the days. So anyway, so this is going to be, the first few modules of this course are going to be a crash course in building a software rasterizer. So again, it's one of my tools for teaching you graphics, C++, the math behind the computer graphics, all the foundations, okay? And, I'm sort of saying that, hey, I'm taking you back to the 90s. That's because, well, the 90s was before you really had dedicated graphics cards in your machine. So if you've ever built your own PC, likely you've installed a graphics card and physically inserted it. If you've bought a laptop recently, you probably have some sort of dedicated or integrated graphics card that handles all of the rendering, all the drawing of these scenes here. Okay, but back in the day, back in the 90s, most of the time in the 90s, up until about 1996 or 7 or so, everything, all the programming, all the logic, the game, the physics, AI, and the graphics were all done on the CPU. Okay, so that means you had a lot of work to do on a CPU, and of course then CPUs weren't as fast then. Okay, and folks often created their own graphics APIs as well from scratch. So we had still OpenGL back in that time, but people would still write their own library. They didn't want to depend on it because the graphics hardware maybe wasn't as reliable, and the APIs maybe had bugs or didn't support all the different graphics cards. All of AMD, which is ATI at that time, and even NVIDIA. It was hard for these companies, which were much smaller then, to support all of those things. So anyway, the fundamental techniques used in software rasterizers are still the same thing that hardware, your dedicated hardware, is doing and communicating with these APIs like OpenGL, which we're going to learn. So we want to learn some of those fundamental techniques. Okay, so again, why learn the foundations? My answer is here. A couple of things. As I mentioned, the education portion of it, so you can really understand what's going on with hardware accelerated graphics. I really just think it's essential because if you understand the foundations of something, you can build off of it rather than looking at graphics programming as just a black box. We really want to understand how things work. And during this time, it's a little bit safer to start learning some C++ stuff. Even today, though, offline rendering, so for folks who are going to see me in the ray tracing class or these other things, is still a very widely used technique. And even doing the software rasterizing stuff we're going to do in real time can still be used in some specific instances. Okay, so understanding or the ability to build our own pipeline is important. Sometimes games include a fallback mode. So if the hardware fails or isn't available, or you're otherwise on an embedded device, so some smaller device that doesn't have a GPU, this is what you need to do. If you go to work at places like Intel or AMD, Qualcomm, any of these places, IBM even I think does some GPU stuff now, but oftentimes, before the hardware is built, they have to emulate it somehow. So they're still doing that on a CPU, and they'll have a really big sort of CPU that doesn't look like anything that you put in your machine. It hasn't been sort of minified yet, but they'll have to have some sort of GPU emulation software. Okay. The other things, again, it's kind of cool if when building your own software pipeline, if you have complete control of everything that's going on. You can debug it too, because it's easier to debug things on the CPU, right? That's why we also did the emulation step as well. Okay. And the simplicity is nice. There's no libraries or anything, no drivers, no hardware or anything to download, right? We've already, seen how difficult that can be to rely on third-party libraries sometimes. And SDL itself is a really good one that's used by many folks. And we can see just the setup sometimes can take time. Okay, and it's fun, this is a fun way to learn things. So how I want to introduce this is by introducing what's called the fixed rendering pipeline. Okay, sort of illustrating what's going to be done in our software renderer. So we have this pipeline here of one stage to the next thing. Okay, so let me put this in terms of history a little bit. OpenGL 1.5 and earlier used what's called a fixed function pipeline. That means that you start off with a single vertex in your world here, and it's going to be transformed through all of these stages here. Every single vertex. If you have 1,000 vertices, all 1,000 pass through this, pipeline one after the other in sort of a linear fashion. Okay, this is a sort of the pipeline, and we say it's fixed because everything just goes one step after the other. We can't really change what happens at any point or change how any of these steps in the pipeline work. Okay. And for us, we're going to roughly follow this. Okay. It's a little bit easier to follow. And so we're going to start off with, just some vertices in a 2D or 3D space, just plotting points somewhere out in the world. And then we're going to process these vertices and connect them. Okay, that's what the primitive processing is going to be, sort of saying, hey, we have A, B, and C here. How do we make a triangle out of them? So we'll assemble them, and then we'll fill them in. That's what rasterizer means, sort of shade them in a particular color. Okay? And then we're going to work on, not today, but in modules sort of 2 and 3, transforming and lighting our rasterizer. So here's a little preview of a 3D render that I made. It's just of a wireframe. It's not filled in, but you can tell it's a box here, just a wireframe box. And that would be part of the transformation and lighting stage. Okay, it's not really lit, it's just bright here. And then when you're at the end of your pipeline, eventually, right, this is drawn out to the screen, okay, so that you can actually see it. So this is stored in something called a color buffer, and then the final sort of buffer that's output to your screen or your window that you're looking things at is called the frame buffer. Okay, so you can leave like a window frame if you want, but that's what we are seeing here. Okay, so with that said, let's go ahead and explore our sort of software rendering pipeline here as we learn some fundamentals. Now, there are some more things involved, so we're going to talk about this a little bit more in module 2 and 3, but basically this idea of how do I take something 2D here. We'll look at this or a version of this diagram later, but how do I take some point that I plot and make it look 3D? And you'll see there's lots of different transformations that go on, and there's a few steps here. It doesn't mean it's complicated, but we'll want to break this down into the steps here momentarily. Okay, in our next 2 modules or so. Okay, so let's just start from the beginning in our software rasterizers with our vertex data. Okay, so the things that make up just our points. Okay, and then we'll talk about line segments and triangles. Okay, so let's just talk about these things here. So you may or may not be able to believe it. Here's Gollum, the character from Lord of the Rings, the books or the movie, however you know it. But if you look at this figure here, this 3D model here, you can see that he's just, we've sort of traced lines here, but Gollum's just made out of individual points, and then those are connected to make some primitive. In this case, if you look really closely, it's actually a quadrilateral, but that would get split in half to a triangle. But that's it. And just using triangles, you can represent nearly any shape. You can approximate any shape with very good accuracy by just making it a triangle. Okay, and it's not always immediately obvious, when you look at this character. Maybe more the one on the right, the sort of lower resolution version. You can sort of see the hard edges of the triangle, but when you look at this one, it's pretty smooth. It looks pretty good. It's representative of something very organic and real looking. Okay. Okay, so of our primitives, points, and we usually just call them vertex because we're talking about geometry in this class and graphics. But a vertex here is usually just 2 or 3 values, an x and y position or an x, y, and z in a Cartesian coordinate system, and they're just plotted. And if you plot enough points here at the right locations, this would be called a point cloud. You can represent a 3D figure, right? You can tell that this is a Tyrannosaurus Rex here, okay? Now, if I connect 2 vertexes together, or 2 points, they create what's called a line segment, Okay, and the order doesn't matter if I connect point A with B or point B with A. It's the same line segment here. Okay, so here's the 2 points here, and I'm plotting them on an XYZ plane here. So X here, Z, and then Y in the up direction, and here's our line segment plotted in 2D here. Okay, and by connecting them and creating this line segment, it creates a relationship between our points. Okay, we're saying when these, has a definite sort of endpoint here, and it's a segment here. Okay, we don't work with lines in graphics; we work with line segments. All right, so the next primitive is the triangle. So that's made up of 3 points or 3 line segments that are connected here, and then we form a triangle. Okay, and then our goal is, once we have a triangle, is to then shade in the triangle or filled in with color. Okay, we can think of it as just filling in the pixels with color here. So you can see how this is done. There's 3 line segments that are put together. And then this sort of algorithm here, starting from the bottom to the top here. You can see the bottom triangle here, and then the top triangle here. And then we're sort of just shading in one at a time here. Anytime in blue here, we have a point that falls within our triangle here. Okay, so we're actually dividing this triangle into half here, a top and a bottom half. We'll talk more about that later, but this is the basic idea. Once you have a triangle, then you can shade it in, and then once you've shaded in enough triangles and position them in 3D space, you can see 3D figures. Okay, now an important property of triangles and why we are using them in computer graphics is one, they're simple, right? We just have 3 vertices, 3 line segments. We know what angle the insides add up to for this shape, 180 degrees, and the shape itself is planar also, which is really the important part. Planar meaning that it's flat, right? If you draw a triangle, if you just cut out a piece of paper and make a triangle, you can't bend it, right? By pulling one of these vertices. Okay. I'm trying to see if I can do a little demonstration here. If I just capture something here. So here I have made a, I guess you can't see it, but it's a triangle here. Let me move it over to the side here. A triangle over me. Now if I pull one of the vertices back here, it pulls the whole shape, right? It's going to remain a flat shape here. Okay, so you can kind of see it. Sorry for the camera work, or do this sort of experiment here, but again, if I pull one of the vertices, it remains flat. And that's important for us because then it makes it really easy to shade in versus a sort of curved surface or something that's going to be wavy. So triangles are really about making things easy for us as the graphics programmers, easy on our hardware because it's very fast to just shade in something that's going to stay flat like this triangle here. Okay, and we're getting some kind of cool color correction here. Anyway, here's just another example here of some different landscapes here, and you can see the sort of wireframe projected over them. You can see this character here, this scary guy here, and the wireframe model of it with a texture laid on top of it. We'll talk about how this works. And then even scenes, again, where it's hard to tell, where it's not immediately visible, that there's triangles here, you can see them. Okay, but by the time you combine all the different lighting and shading here, you can see things being taken off here, right, with no lighting. Then you can really kind of break down the scene here. It's kind of interesting to think about here when you're playing a game or watching a movie and you can see the triangles or some of the graphics effects. Okay, so a little bit more on just triangles and rasterization. This, again, process of filling things in. Here's sort of the big idea. The main thing that we need to achieve is to figure out how to rasterize or fill in triangles, okay? So we need to figure out how to compute which pixels to shade in a projected shape, okay? So our triangles is what I mean. So, and if I rotate that triangle, how does that change here? Let's see if we can do another live example with my triangle, my sort of interesting lit here triangle. But as I rotate it, you'll notice that there's less pixels to fill in if you sort of think about it over me here. So here it is, and then as I rotate it and transform, it's a different sort of projection of that shape. Or if I move it back, right, there's perspective, so it's getting smaller. And I'm keeping it over myself so you can see it, but that's the idea, right, with our transparent triangle here. Okay, so and another analogy to think about this is when you're creating these line segments and points here, sort of think of it as looking through a screen window, or if you have a screen door at home. And the shapes that you see outside, you're just filling in little pixels or little squares in the screen window for what you would want to shade in to represent that shape. That's what we're essentially doing, right? Our machines, you guys can't see the slide here. But our machines can't, on this diagram, here's the screen window that we're looking through. Our machines have a finite sort of resolution, right, versus the real world where things are pretty sharp when you look outside. But we've got to sort of approximate these shapes by just filling in the pixels here, and we'll approximate the shape of a triangle, okay? And from a far enough distance, or if we have enough pixels, this will look like a triangle. Okay, so the two main things we need to figure out if we want to draw and rasterize a triangle is how to draw a line first off, and then again approximate that line with by shading in pixels here, and then sort of repeat that process here. Okay, so here's just drawing a line segment, drawing sort of 3 line segments, and then filling in the triangle. Okay, so how do we fill in a triangle? Okay, well, we've got to project the triangle onto the screen in some way. Okay, so we're going to use something called a projection matrix to help us with this, to help give us perspective. Again, let me give my very simple demo here, right? If the triangle is very far away, it's small, and as it gets closer, it gets bigger and bigger and bigger. Okay, that's something that we need a projection matrix for. We'll talk a little bit more about that. That's where some of the math is going to come in. But once we have the triangle, which is what we're going to assume today here, we need to loop over all the pixels in our screen. So pretend this is our screen, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, roughly 13 by 13 here. And so loop over each one of those pixels and determine, does our shape here, what color is this triangle? And if it falls in a box, should we fill it in? You know, if the majority of this shape, of the pixel in this shape falls within this boundary, then filled in, okay? My question to you is, does this seem like a fast or a slow process? And I wonder if we could speed it up. I'll give you a moment to pause and think about that. And if you took a moment to pause and think about that, well, the answer is, so long as our screen's not entirely filled with triangles and we don't have to, sort of repeat this process over and over again, this can be a pretty fast process. And it's very easy to parallelize as well, because it's sort of a separate problem where we're just looking at every triangle in our screen, figuring out for each of our pixels, does a triangle fall within that pixel here? So it's a very easily parallelizable problem. We can make it complicated, so depending on how you thought about this, your answer may or may not be aligned with mine, but overall, we're just doing this for every triangle in our scene. Okay, this is going to be opposed to a technique called ray tracing, which we'll discuss a little bit throughout the semester, but there's a class dedicated for that now, where we have to essentially cast a ray on every pixel. So that's what's going to be different about ray tracing, and that tends to be slower. Okay, so let's go ahead and move forward a little bit just to this next step of transformation and lighting. Because we sort of skipped this step, right? The whole transformation, and what if I want to rotate a 3D shape? How do I do that and sort of represent it in a 2D screen? What happens if I have a really big triangle? What happens if I have a light source? How does that change how we shade in a triangle? What if I apply texture to it? These are going to be some of the challenges that we address later. Maybe not texture mapping, but at least the rotation of a shape and then shading in of colors, okay? Again, there's different ways that we can optimize this process. So just an aside, by drawing a little bounding box and just checking within this smaller box if we have any triangles here. Again, that can be efficient. That's a way that we can sort of parallelize things. And one of the things that we also are going to have to figure out is sort of this visibility issue in our rasterizers. So the question I'll propose to you is, if I have a bunch of these triangles and they're overlapping other triangles, how do I figure out which one is visible? And I'll give you a moment to pause and think about that. And if you've paused and taken a moment to think about that, this is one of the future challenges we're going to face. I call this the hidden surface problem. You'll probably see a version of these slides or similar figures later on. And what I mean by this is if I have two surfaces and they overlap, how do I know which one to draw? Okay, which one shows up on the screen first? And one potential solution for this is something called the painter's algorithm, which goes as follows. It's sort of, if you've done any painting or drawing, you typically draw, if you're going to draw a landscape, you draw the background first and then the objects in front of that, and then eventually the foreground, right? So you draw the furthest away objects first, and then you draw the other objects after. And then that sort of gives you an order. But my question is, again, to think about that, and why we'll need to think a little bit more about this visibility problem is, does the painter's algorithm always work? Give me a moment to pause and think about that. Well, the answer is, as you can tell in this figure here, if I have sort of this weird sort of blue shape overlapping the red, and then the red overlaps the green, but the green overlaps the blue, this sort of weird pattern here, this is a sort of cyclic relationship here that sort of breaks the algorithm. So it can't sort of do this on a per object basis to sort of say, hey, we're going to draw the first thing, the blue object first, and then the red, then the green, if they're sort of overlapping each other in this sort of cyclic way. But there is a solution, though, a simpler solution, in which we can use something called a Z buffer or a depth buffer that computes per pixel of every pixel that we have which shape is in front here. So this triangle is in front of A, is in front of B, which is in front of C, and then we just record the distance from that pixel in a buffer, and then we know to draw that particular shape's pixel here. Okay, so OpenGL does this. It keeps track of the distance from 0 to 1. It normalizes in that range here for each object, and then we know whatever's in this buffer, if it happens to be that A has the lowest value in the Z buffer, it must be the closest. So for this particular pixel, we draw the triangle here. Okay. So every time that we draw an object, the Z buffer does this test to see which pixel is closest. The CPU or GPU can sort of do this mindlessly, so it's a relatively cheap algorithm to figure this out. That's going to be a theme in this class. You'll see that we like to use very simple algorithms in computer graphics because they have to be fast and you have to be able to do them in hardware as well. Okay, so here's just an example of this is a game here, and the lighter colored pixels, this is the actual Z buffer being drawn, but the lighter colored pixels are closer to us and the darker ones are further away. Okay, just to sort of represent that. Okay, so also to note during this stage, and what we're doing and where we're storing these different pixel colors, we have something called the color buffer. We're actually storing the pixel colors. Okay, so you might combine something called the color buffer and the Z buffer together, and just have different arrays for those, which you're using to build one frame, and this is called the frame buffer. And then decide for that particular frame which pixel is closest and what color it should be. Okay, and that's the final thing that you're drawing to your window for the users to see. Okay, so a little summary of rasterization. Now that we have an idea of how to solve this visibility problem, we have the key components of our rasterizer, right? We have a place to store our pixels, the colors, how to test which one's closest, and then how to figure out how to draw our triangles, project them, and ultimately output our triangle or whatever we are drawing in our 3D scene. Okay, so let's think about applying what we've learned here. And if you need a little break after that just to review some of those topics, go ahead and do it, and we'll run on to our next thing. Alrighty, so if you're giving yourself a little break, let's go ahead and continue. And this is going to directly lead us into our lab, which you'll be working on today, Lab 2, and give you a little bit of a walkthrough and a review of C++ as well. Okay, so again, we're focusing on drawing lines and triangles. That's our goal here. Again, because as I mentioned, every sort of 3D object is made up of triangles, right? If you look closely at Mario enough, this visualization just has them as quads, but these are broken into triangles eventually. And that's our foundational primitive, okay? So what we're going to be building is a software rendering engine. It's called GLRenderer for the Great Looking Renderer. That's what we'll be building here. And we're going to be sort of talking about some design decisions first for our render. And eventually in this course, we are going to use hardware accelerated graphics. That's what most folks use. That's probably what you'd use on a job. It sort of depends. You could be on the other hand where you're implementing OpenGL from scratch. Again, someone has to implement those hardware things at Intel and NVIDIA and all those vendors. So it is true, a lot of this software rendering stuff you'd need to learn. But eventually we do want to learn OpenGL here. So for this little project that we're going to be working on in the next lab and probably the next lab and assignment, we'll make a few key design decisions that don't want to tie us to any specific API. We're going to be using SDL a little bit. We're going to name things similar to how they are in OpenGL so that when you transition to OpenGL later in this class, it'll make things easier. So I'm going to sort of be mimicking how OpenGL works in its old pipeline. Okay. The code that I provide in some of these things are going to be intentionally simple. They're not going to be the most performant thing. They're not going to be a fancy C++ thing, right? This isn't the C++ class, but they're going to be for clarity and ease of use. And that sort of goes with a lot of things in this course. We want sort of clarity so you understand how to build something, and then we can optimize it later, okay? So it could be very fun to do a data-oriented and very fancy and performance software rasterizer, but that's not the primary goal for this course, okay? And you might enjoy this during the first half of the course and want to continue on building onto this project. That can be a final project in this course. It's something to think about, and it's never too early in this course to think about what your final project might be. Okay, so moving on here, we've learned a little bit from your first homework assignment, so please look at that if you haven't already, about the PPM format. Our PPM images, they store a red, green, and blue components. For red, green, and blue make up a final pixel color, respectively. Occasionally you have the alpha channel as well stored there, which represents the opacity or how transparent an object is, or excuse me, a pixel is in an image. Okay, so if the A value is 0, that means it's transparent. If it's 255, it's fully opaque. You cannot see through it. Okay. So for us, all we're going to need for our lab is the ability to draw a PPM image or some sort of image type. I provide some sample for that. So that'll be very helpful in your homework, I guess. But this is going to act as our color buffer or part of our frame buffer for which we can draw on. Okay, in the future, we'll use SDL2 and create something that's moving in real time. But for now, we just want to be able to draw triangles. Okay, and we're going to display them as PPM images. So as long as you can view or open a PPM file, you can see what your progress is. Okay. And then we'll have, some other things later on in our software renderers, like ways to clear each frame and redraw it and so on. Okay, so our C++ software renderer, we're going to create something that looks like this, right? You can see a red line that you're able to draw, and then you can see a shaded in triangle here. Okay, so that's roughly what we're going to be building, and I want to walk you through how to do this. And do it with C++ and with a little bit of math here. Okay, so how do we draw a line segment and a triangle, which is 3 line segments? Okay, so again, we got to start with the basics, what a vertex is. So triangle consists of 3 line segments, right? We've talked about that, 3 sides. So how do we represent this in C++? Well, in C++, we can use something called a struct to create a custom data type. And we're just working in 2D for now, so just a vec2 and an x and a y, right? This will represent the pixel position that we're drawing at, okay? And we just need integers right now because we're just working in pixels. So the name of our new data type is going to be vec2, and it's got 2 member variables, x and y, representing the pixel position. Okay, and we can modify this. So here we're creating a vec2, my point, and setting the x and y of our vec2 here. Okay, so if we create this point, then we plot it here on a 2D system here. So it would fall somewhere here, 50, 100, something like this. And if we plot a second point at the origin, 0, 0, we get a second point here. Okay, now that we've plotted 2 points, we just need to be able to connect them. Okay, then we'll have one side. If we repeat that, plot another point and connect all the sides, we'll have a triangle. Okay. Now in C++, one thing that's we can do to make our life a little bit easier, we're going to be creating a bunch of points here, is we can create what's called a constructor so that we don't have to individually set all of these member variables for our point here. Okay, so in C++, you have something called a constructor. That's called when you initially create the object. And then you can create another constructor here where you populate x and y with these values. So x will be set to whatever you pass in, underscore x here, and y will be set to underscore y. This is called an initializer list, and it's one way to set member variables. You could alternatively just set x equal to underscore x and y equals to underscore y. That would also be fine. Okay, so let's figure out how do we draw a line segment at this point, okay? So for our draw line function, we need 2 points, or vertices, represented by v0 and v1, so these are 2 vertices. And then we need a canvas to draw on, which is just our image, okay? And then the color of the line. So 4 parameters here, our vertex, each of the 2 vertexes, the image that we want to draw on, and what color we want that line segment to be. Okay, so this we've covered. Let's talk about our canvas and our color next. Okay, so our canvas, or where we're drawing to, the coordinates are actually flipped from what we're used to on our Cartesian coordinate system. Okay, this is a convention. 0, 0 is the top left corner. And then as we move down, the y value increases. As we move to the right, the x value increases, right? So this is sort of our coordinate system in the window space when we're drawing on a window. If you've ever used a Paint program, a Photoshop, Paint on Windows, you might have noticed the coordinates in this manner, okay? And we need a canvas. Again, a canvas is just going to be an image. It could be a PPM image, TGA format, whatever. I think I give you PPM, even though I call it TGA. So this is implemented as a C++ class. Classes are almost the same as structs in C++. The difference is by default, the visibility of everything in a struct is public. In a class, everything is private. So you have to specify public at the top here for your constructor to make it available. Okay. A class in C++ is just a collection of attributes and behaviors. Okay, so your behaviors are your member functions here, whether they're constructors, destructors, or member functions here, and here's your attributes here, just the data that belongs with it. Okay, so class itself, though, is a specification for how instances of that class, known as objects, operate, right? So here's our blueprint, and then we'll create at least one canvas which we can draw on here. Okay, so here's our new custom data type, the TGA class. Okay, and it's got a unique name, and we're good to go here. Okay, so just some other notes here. Usage of member variables, and again, is controlled with public, private, and protected. And the same thing for member variables. So we can write this multiple times. Anything that comes after it that will either be publicly accessible or not accessible if we make it private. Okay. All right, so we can create objects of our class. So again, canvas is an instance of the type TGA. And here's a constructor where we're explicitly setting the width and the height of our image here. All right, so in this lab, you're going to see a structure with multiple files. Now is a good time to just go ahead and open up the lab in the appropriate class. Let's see here in computer graphics. So here's lab 2. So you're going to see the source file here. There's 2 sources, the main here, and then an image class. And then an include, we'll have a couple other files here. The header files are the sort of blueprint here for us. Zoom in here. Again, just the class here. And the source files are the implementation. So how we do things in that class, right? The actual constructor, destructor, member functions, right? If we compare and contrast these, this is just sort of the declaration that says, hey, this exists. It's part of the image class. But now we have the implementation here in our C++ file. Okay, so you're going to notice, again, several of those files there. Header files are things that end with .h, HPP, or h.xx. The implementations of those interfaces are just the regular C++ files. They usually end with .cpp or .cxx sometimes. And usually, and I'll follow this pattern in the class for the most part, you'll have another file here called the main.cpp. There's usually no header with that, which is just the source file and has the main function. Okay, so again, here's just a reminder on that, the header file implementation. The header file here at the top is the interface, and the implementation here below is the CPP file. Right, it's where you have your constructor, destructor, and implement them. Okay. Here's a little example of, on the left side here, you've got a header, a C++ file here, your main, and then how to compile that. So if you're using the Clang or G++ compiler, you type this in, C++ 17, etc. And then each of these C++ files are what get compiled, and then what we output that program as, class 2 here. Okay. And it's important to realize you don't compile the .h file. It's included, you'll see here at line 2. So when I include something, it's essentially a copy and paste. So it's just copying and pasting this declaration of this class and sort of, what it's got part of it into this file here. That's essentially what it's doing. And it'll only do that once if I have what's here at lines 1 and 2 and line 14, which is called a header guard. Because I'm defining this symbol once here, the first time it sees this file. I say if it's not defined, define it, include, and say somewhere in our project that this class exists, and then end if here. Okay, that's something called a header guard if you want to look it up to get a little bit of help on that. Okay, so recall, I mentioned this early, but C++ also has structs, and remind yourself for a moment what's the difference. All right, if you've taken a moment to pause the video and think about this, again, just remember the default privacy level is public in a struct and private in classes. And this varies from person to person, but usually I'm going to use structs in this class as just a plain old piece of data, or it just contains a few member variables, and then a class as an actual thing with member functions or methods. Okay, now why we like classes in this class, why we're going to see them, is they nicely encapsulate things. The intricate details are sort of hidden from the user, and we can sort of use them again as a blueprint. It's a nice way to think about things, especially in graphics when we're working with sort of physical or virtual objects. It sort of makes sense to go with this object-oriented style. Okay. We can also build on classes when we use inheritance and some of these things, or composition. We'll see some of those techniques, in this class just a little bit. Okay, so again, intermingling or adding some C++ throughout this. Let's get back to where we left off here. Now that we have this sort of image class and understand what a class is. Let's figure out how to draw here. Okay. Okay, so our canvas and is this array here. It's really just an image here. It's the image class or TGA class I have in the slides here, holding all the values here. Okay, so the 0th value here in our array is the first set of R, G, and B values that'll specify what this pixel is, and so forth. Okay, so each individual pixel, whether it's at 0, 0, 1, 0, etc., holds an RGB color. So we need a structure for that, color RGB, that holds R, G, and B. It's an unsigned char because that holds a value between 0 and 255. That's all we need here. So each pixel, again, stores an RGB value. Again, your assignment 1 covers a little bit of this, but just as a review on how color works or how it's represented in our machines is something like this. The intensity of a color value between 0 and 255. If I add more green, it becomes more green. If I fill all these up to 255, it becomes a white color. Okay, so we're going to see this get more green because green's the only intensity left here. Okay. All right, so a little goal check here. Let me pop in the screen and talk to you guys for a moment. We're learning some C++. We're learning we can plot points on a scene here, just as a set of X, Y things. We create a little struct for that. We understand what a pixel is, a set of R, G, and B values, and we're going to modify those values on an image, okay? And that's what's going to ultimately draw our scene, okay? All right, so how do we draw a line here? Here's one of our big goals here. Well, we have an algorithm for that. Bresenham's line algorithm. So this is the thing I alluded to earlier with Michael Abrash, the chapter there. But the idea is, again, given 2 points in a 2D coordinate space, figure out how to shade in all the pixels between those 2 points. Okay, so this is the process of when we're filling in pixels, again, that's called rasterization. And we're going to start off by doing this with just a line segment. Okay. Okay, and this problem's been largely solved for us. Again, we'll use something called Bresenham's line drawing algorithm. There's another algorithm called Wu's algorithm. There's probably a bunch of other algorithms. Maybe you could invent one as well, but they're generally well known here. Okay. So provided above is the function declaration for drawing a line here. Again, the function definition is going to be in the next slide here. And there's a really nice talk here for Bresenham's line algorithm. So this is one of the links in your resources to watch. I'm just going to click on it. I won't play it so we don't get any copyright issues. But the idea with this talk here is they're going to walk through how to actually draw a line. So things like calculating the slope between 2 points. So once we know the slope and once we know the starting position between X and Y, we can calculate how to draw lines. This is a really nice talk here with Jen Schiffer here explaining some graphic stuff here. I forget what the you better listen part is here, but this is how to draw the line here. Okay, so let's go ahead and proceed forward a little bit with Bresenham's algorithm. But there is something I want to talk about here because this function looks a little bit weird to me. It's going to be a little bit weird if you're new to C++ as well. It's got this TGA and then an ampersand here. Okay, so this is our image class here, ampersand image. And this is probably new for people who haven't done C++ at all, okay? So to talk about this, we need to talk a little bit about memory management in our C++ programs here, okay? And here's sort of the basics, the crash course. The reality is memory is typically talked about being allocated in 2 places. Usually we talk about stack memory and heap memory. So stack allocated data is things like our local variables or arguments from functions, things that are going to only live a short amount of time. Right, your local variables. Heap data are things that are allocated with new and delete, or if you've used C, malloc, and free. Or even in Java, when you use new, that's allocating something on the heap, something that's going to be long-lived, and it's intended to live until you explicitly call delete on it in C++ or free in C. Okay, the next thing we need to talk about, though, is pointers and how they're used. Okay, so let's just talk about memory again a little bit. with this in mind, let's assume I've created some variables of different types. Integer to chars. Depending on the type that we create, it takes a different amount of memory. So integers are 4 bytes, for example, so 4 boxes here. If this is my memory here, this grid. Chars are 1 byte, so 1 box here, each of them. Okay, so if I zoom into one of the boxes here, each of our variables has a piece of has a value and a location. Okay, associated with it. Okay, so here's the memory location. Now, if I want to access that memory, how can I do it? Well, this is one of the uses of the ampersand operator. This tells us which box the memory lives in. So in this little program here, you can try it out. If I create a variable x here, set it to 42, and then I want to know the address of x, I just put an ampersand in front of it. Okay. Then when I run this, it'll say x's address is at this location. Your computer is going to say something different because you have a different computer with different memory, but this is where x is currently located. Now here's something else to consider with memory, how it's sort of passed around in functions, okay? So go ahead and take a moment to look at this program and let me know, what do you think x is here at the end of the program? So when it prints out x. And if you've taken a moment to pause the video and think about that, right? So we have this main function. I set x to 42, I call set value. Passes an x here into this function, and then I say, okay, a is equal to 9999, and then I print out the value of x. Well, if I'm passing in x here, right, a is sort of that value here, and I'm setting it to 999. Well, the answer is actually x is 42, because we're doing something that's called pass by value in C++. We're actually passing a copy of x onto the stack here. Okay, so by default in C++, if you don't specify anything, if you just say, hey, I'm passing an integer here, that's going to make a copy of that value because it doesn't know if you want to modify x here. C++ isn't smart enough to figure that out for us. So it's just copying that value here, okay, at line 9. So that's why when we modify it here, we're just modifying the copy, not the actual value x here, okay? Now, C++ offers us something else where I can put an ampersand here. I can actually put it next to int here or next to the variable, it doesn't matter. But now take a look at this, or try this example and let me know what you think it is. So if you've paused the video and maybe tried this example, the actual value is 9999 this time. Because this time we're passing by reference this value, so it's not passing a copy, but it's passing an x here. And then it's using a as an alias value, or an alias, so that is, take the actual thing here, x, pass it in and just call it a, but it's really x because you have the ampersand in front of it, and set x to 99999 here, okay? So this time x is 9999. So when you use the ampersand here as a parameter in a function, what it's doing is saying, hey, actually pass in this variable. Don't make a copy of it, okay? Okay, so when we're passing by reference, again, we're passing in an alias to another variable that exists. This is generally the preferred style in C++, and it's considered safer than passing around pointers, and we'll talk about pointers in a moment. Okay, there's different ways to pass around data in C++, and they're sort of summarized here. I've got a little example here. You can pass by value, which is sort of the default, pass by reference with the ampersand sign, and you can pass in a pointer here. Okay, which is also passed by value, but just another way to pass a variable in. We'll talk about pointers in a moment. Okay, so back to this. Now we understand what this thing is going on. So when we draw a line, we're actually modifying whatever image we're passing in. And that sort of makes sense because we're going to be drawing a lot of lines, and we want to make sure we're working on the same image throughout our program when you look at the support code. Okay, or better yet, let's actually just look at the support code. Let's see what I got for you here. Just show you. In main here, where you're calling draw a line. Here, for example, you're modifying the same canvas. Okay, so if I'm going to be drawing lots of lines, I want to just keep modifying this same canvas that I've created. Okay, here. it's globally accessible, I guess, here. Okay. Okay, so as alluded to, we have another tool. It's known as a pointer. This is another way that we can pass around data in C++. A pointer is just a variable that holds a memory address. The address is the value that's stored in a pointer. Okay. Syntactically, how we do this in C++ is with the asterisk symbol. And that's used with a type to create a pointer to that particular data type. Okay, so let's look at pointers a little bit more. They're going to come up a little bit. So again, what are pointers? Pointers are another data type. A pointer just stores an address. Okay, that is, it's indirectly pointing to a value. There are integer pointers, floating pointers, double pointers, even pointers to your custom defined types. And here are some examples. So here's how we create an integer pointer. Notice it's an int with an asterisk next to it. Floating pointer. It's just a float type with an asterisk next to it, etc. So we could say that's a pointer to an int or a pointer to the float. Okay. So the asterisk next to the type means it's a pointer. What's going on here when we use a pointer here, on the left side here we have a normal variable, which say int x equals 500. On the right side here we have a pointer type that we've created. And pointers store addresses. Okay, so y equals ampersand, the address, remember that's the second, one of the uses of the ampersand, address of x here. So it's going to store the address in it of x. Well, where does x live? Well, x has its value, 500, but it's also stored somewhere in memory, 1001 here. So if I point to x, I'm storing the address here of x. Okay, that's how pointers work. Okay, so here's some pointer examples. It helps if you type these out and try them. But here's how we create a pointer, again with the asterisks. Sometimes I'll put p in front to indicate as a prefix to this name that it's a pointer, just to remind myself. Okay. We want to initialize the value. So x equals 5. Pointers, we just make them null if they point to nothing. In C++, we use null pointer sometimes too, if we're using modern C++. And if we want to point to x, again, we put the ampersand x here. So it points to x. And we can verify that p of x points to x by printing it out. This is in C, but you could do std cout and then the address of x and then p of x here. And that would give us the address where x lives, address of x, and then what p of x stores. Remember, pointers just store addresses. If we're just printing out p of x here, well, what's p of x? It's the address of x here. Okay. Okay, so that's great if we can store addresses, but how do we make use of them? Well, if we want to actually retrieve the value, that is, retrieve the value of the thing that lives at this memory address, which is x's value here, we dereference the pointer. Okay, so we do that again with an asterisk. That's where it gets a little bit complicated. But here's what we say when we're dereference. Whatever I'm referring to, don't give me the address, because remember, ampersand means address of, or reference, but instead give me the value. Okay, so hence you're dereferencing. Okay, so let's give it a try here. So in this example, p of x dereferenced, if I want the actual value, which is an integer here, %d is the holder for that, I do asterisk p of x. I'm dereferencing the variable p of x here. So whatever I'm pointing to, dereference and give me the value. This gives me 5. Okay, and here's another example question for you folks. What happens if I now dereference p of x doesn't modify x? So let me walk you through this and then take a moment to pause and see or try it out. Int x equals 5. I create my pointer, same thing we've been doing, pointing to the address of x. X's value is going to be 5. But now if I dereference p of x, so p points to x here, and if I dereference and say, hey, the thing that I'm pointing to, set it to 100, well, what happens if I just print out x's value now? So go ahead and pause the video and try this. And if you've taken a moment to pause the video, the answer is x is initially 5, and that is indeed 100. I can modify x through what points to it, because p of x points to x's address, so they're pointing to the same piece of memory, and then I'm dereferencing it and saying, hey, whatever I'm pointing to, change the value to 100. That's the power of pointers, this indirection. I can indirectly access and change some other value. Okay. Okay, so why use a pointer? They're part of C++ here. Well, first off, a pointer, when passed in as a parameter of a function, that's one way to modify values. It's still making a copy, but it's making a copy of something that points to something in memory that exists. Okay, so it's cheap to do that because we're just passing in a pointer, okay, versus passing in a really big struct, so sometimes you'll see this pattern. Secondly, pointers are very handy as a tool just for building data structures. So trees, graphs, lists, these kind of things. We'll want to be familiar with them. And thirdly, whenever we're dynamically allocating memory on the heap, when we use new, we're getting a pointer back to a chunk of memory. So we have to use pointers in that case. Okay. So with that, pointers are a little bit magic when you're first learning or using them, but they're really cool, really powerful part of the language. But they give us, the ability to access and pass around data very efficiently. Okay. And if you just remember that pointers are merely variables that point to memory address, they're not that complicated. Okay. If we just sort of break them down in that way. Okay. So pointers can store a particular address to a type that they're declared as, like int star or int asterisk is an integer pointer. And then you can dereference and get that type of value back. Okay. But they're not that fun in C++ in the sense that we prefer pass by reference when we can do that. But usually, you pass by pointer if you need to allocate memory for that pointer. Okay, so back to business here, because we're passing by reference here. So taking a look at our constructor here, this is an example of m underscore pixel data is actually a pointer, and we're allocating memory here. So we're grabbing a new chunk of memory here. The width times the height of the image, and then times 3 because we need R, G, and B values for each of those pixels. Okay, and then memset just sets it to all the values to 128. Okay, so we got to talk about this new thing though, because we're still talking about memory allocation. And how do we do dynamic memory allocation in C++? Okay. All right, so moving on, we have two C++ keywords to allocate memory dynamically, new and delete respectively. And when you call new, you can do this wherever you want. It allocates a block of memory or asks the operating system and says, hey, can our process that's running have some more memory so we can store more data? That's essentially what's happening with new. And when we're done with it, it's polite to delete the memory. It's also necessary because we only have a finite amount of resources on our machine. So we call delete on memory that we've allocated. Okay. So in C++, we have to manage memory allocation and deallocation by deleting it. That's probably something that's new for you. Why do we have to do this? It sounds like a little bit of extra work, but again, this is the advantage with C++ and why we get a lot of performance in our programs. Okay, this allows us to build our own data structures, also, which is very nice. So data structures like lists and stuff. If you think about what happens behind the scenes, or when you're concatenating strings, this is what's happening. You're allocating more memory, and then to concatenate two strings, for example. So let's take a look at two scenarios where we use new and delete. Here's just an example of creating a new vector here. So I have a pointer here, right? I'm pointing to a new chunk of memory here to create one of these new vectors that has an X, Y, and Z location. And then when I'm done with it, I delete it. Okay, and that's how we use things. I reclaim that memory. Here's another example of another allocation here. And I have a pointer here, so it's going to point to a chunk of memory here. I'm creating an array, though. I'm asking for a new 50 vector 3s here. Okay, so a bigger chunk of memory with X, Y, and Z, X, Y, and Z, enough for 50 floats or 50 vector 3s that have X, Y, and Z. Okay. Now, when I delete this one, I use delete with the brackets because this is an array here, right? I can index into this vector here. So I have to use delete with the brackets, and then I'll delete all 50 of these. If I only just call delete that on the without the brackets, it'll just delete the first vector 3 here. Okay. Okay. So those are the sort of key observations. Is that we have to use new and delete in pairs. That's one observation. The next that it's best to just reclaim our memory as soon as we're done with it. Usually this will be done, the new and delete in our constructors and destructors. When we're allocating this memory, it is again on the heap. So we know its sort of address. We can point to it. We can have pointers point to this memory and so on. Okay. So, and also just pay attention to using the brackets with the delete. If you forget, then you get a memory leak. Here's an example of something not to do. So if you create again with the brackets here, if you forget them, then C++ won't complain, but you'll basically only have deleted the first item here. And then your pointer will point to nothing, and then you'll have 49 integers just hanging out. Okay. All right, and just another note on smart pointers and C++. So this is another feature, I guess, of C++ that you're welcome to use. If you come to languages like Java, again, you're used to not having to use delete. You might forget. So it is possible in C++ to write or create pointers that sort of manage themselves. They have a little bit of overhead. You're welcome to use them. We learned about raw pointers today, but there's such a thing as a unique pointer, such that you can have a pointer that points to just one thing, a shared pointer, where you can have many things pointing to it, weak pointers, which can be reclaimed even if something else points to it, auto pointers, which you shouldn't use, and then of course you can sort of build an abstraction on top of pointers if you want. So we usually call them smart pointers, but here's sort of a class where I have a pointer and I can keep track of how many references I have to it. And at any point, if I don't have any references to this pointer, then I can automatically reclaim it. Okay, so you can implement your own sort of little garbage collector if you wanted to. This is possible, but you can also just use what's built into the language, unique pointers and shared pointers, ideally. Okay, so again, why am I talking about pointers? Why do we care? Well, again, they're going to become particularly important for us because we're going to have to think about memory that we're shipping from the CPU onto our GPUs, right? So here's a GPU on the right. Because again, there are two different devices, so we're going to be passing sort of pointers around between them. That's how they communicate between the data. I have to figure out what data or what chunk of data do I want to copy over to the GPU. So we're going to do this in our software rasterizers. We're going to do them in our GPU programs with OpenGL as well. Okay. So just some words of wisdom if this was too much for you, or if it can be a little bit overwhelming, but again, just remember break things down into smaller pieces, and do take a look at this C++ tutorial, some of the resources that I'm leaving. You can read the pointers and dynamic memory section, and then also get a helpful you can sort of get ahead, or sort of maybe those will be ways to also understand or practice with the pointers. That's how you'll really learn these different things. Okay, and then here's a fun video for you to watch too, just to review with pointers and how to use them properly in references and so on. Okay, maybe someday someone will make a graphics project with this guy Binky here that does a better video. That would be kind of neat. Final project idea. All right, back to graphics here as we're moving along here, because we're still trying to figure out just how to draw our triangle here. Okay, and we're sort of wrapping things up too. But so as mentioned before, the majority of our real-time graphics programs draw things again in triangles, and we have 3 line segments that we can draw our triangle with. Okay, so for our triangle, if we want to draw it, well, if we have a point 0 and point 1 here, vertex 0 and vertex 1, in order to draw a triangle, I draw that point from 0 to 1. Oh, and sorry, we need a third line segment. Excuse me, we have a third one here. So 0 to 1, 1 to 2, and 2 to 0 would make a triangle here. 0 to 1, 1 to 2, 2 to 0. Okay, so that's that's what we need to do in our triangle draw function, okay? And that way we can at least draw wireframe triangles. They won't be shaded in, but we can draw the line segments, and that's really all there is to drawing the triangle, okay? So here's a sample of this. Let's create an array of data to store our vertices. Okay, so here they are. We're going to have 3 points here in our triangle, 3 vec2s, which represent the points or the vertexes in our triangle here, 0, 1, and 2, and we'll pass that into our triangle function. We're going to draw our triangle on our canvas, and we have a color here, red, for R, G, and B here. Okay, and then we'll output that to our canvas. Okay, and if we do that, that'll be enough to draw a triangle. Okay. Arrays I haven't talked about explicitly, but in C++, if you're not familiar with them, they're similar to how they would be in Java, but they're just a homogeneous type, meaning that everything in it's the same type. So when I create this try array here with 3 elements in it, they're all vec2s, as you can see here, and I'm initializing them. Okay, and we index into arrays, they're 0 indexed, and the memory is contiguous. Okay, so one element follows the other in memory. Okay, so here's our triangle. I have another piece of code here to just draw a line segment too, but here's what we drew. Okay, but alas, this triangle is a little bit boring. How can we fill it in and rasterize it, right? Because we want to actually shade things in and give them some more detail. Okay, and this is your task for lab. Okay. So your algorithm is going to be able to need to draw any triangle as well, not just equilateral triangles, and shade them in. Okay, so let me provide you with at least 2 strategies to do that. The first strategy that you can use, and I talk about this and provide some resources in the lab as well, is filling in a triangle with a flat top or a flat bottom. Okay. So what does this mean? So if I have this triangle here that I'm trying to draw here, I can separate it in half by figuring out, I can sort the points here, y1, y2, and y3 respectively for each of the vertices. I can sort them and figure out which one's at the middle, okay? And I say, okay, whichever one's at the middle here, I'm gonna create a 4th point here, just draw a straight line across from it. And then I have 2 triangles that are separate here, okay? This bottom triangle and this top one. I'm calling it the flat bottom triangle and the flat top triangle because the top's flat and the bottom of this triangle is also flat. Okay, the slope is 0 between these points here. So then I can figure out how to split this triangle in half and work with 2 sort of easier triangles here. Okay, and then I just figure out, well, what's the slope between V2 and V1 here? Okay, so this is the slope here. And what's the slope between V3 and V1? If I figure out that slope and this slope, well, at this point here, let's say I bump up a little bit here, then I just draw across here until I meet this point here. Okay, and if the slope tells me, hey, move 1 to the left or whatever, and this one tells me, hey, move 2 to the right, then that's my new starting point, and I draw across here. And I just draw line segments across here, right? We know how to draw a line. You'll be given that. Then you can fill in your triangle. So that's one way to do it. Okay. The second strategy is to find from your triangle here, you compute a bounding box. So that is a box around the triangle here. Okay, this is kind of a cool trick here. And then you're going to do a test in this square, okay, if a point falls within this triangle. Okay, so it's going to be a little mathematic technique for this. Okay, so how do I compute the bounding box? Well, again, you have the x's, the 3 x points. So the greatest x point and the smallest x point is your sort of left and right of this box. And same thing with the y, your lowest y point and your highest y point are the top and bottom of this box. So that's how you have this box structure here. It's a bounding box. Okay, so you know where your start is, where each of the 4 points would fall. And then this test to see if a point falls within a box. How do I do that? Let me click on this recommended resource here. So what this is the barycentric algorithm. And let me put a pointer in the slide here, just so it's a little bit more obvious. Okay. Oops, I guess it, let me just type it out here. Barycentric algorithm. And what this is, so here's again how to compute the bounding box. So you can translate this into C++. But there's a little trick here. And this is going to be using a little bit of your linear algebra, and we'll talk about this a little bit because you can use either approach for this lab. I don't care. But if you compute a cross product, so here's your vertices here. And you're going to just iterate through all the points of the bounding box. So all of your x and your y points. Okay, this box you can think of like a 2D grid here. So you're iterating through all the x's, all the y points here. And then what you're doing is going to be using something called a cross product here. So there's a little bit of math here. And figuring out or testing, again, if this pixel falls within the triangle based off of the boundaries of the vertices here. Okay? So it's a little bit of math here. And let me go ahead and just show, there's another really nice visualization of this, what we're doing here. Let me stop the volume here. But if you have a point here that you're testing here, this is another algorithm for it, which is kind of cool. And you're just testing all these points in the algorithm. Here's another way to compute sort of if a point falls in a triangle, which is cool. So you can also use this strategy here. This is a really like computationally efficient strategy here. Let's see, I think he reduces this a little bit, but let me go ahead and link this as well. I think this will be a useful resource, and the visualization's really nice for what's going on here. Let's see here, another visualization. So you can take a look at that. Okay, so those are a couple of strategies for rasterizing or filling in your triangles. Okay, so note again on graphics algorithms, I think it's really cool. I mentioned this briefly, but everything overall is using a simple trick or something that is relatively efficient. It takes a little bit maybe to understand the ideas too, especially the first time when you're looking at it. But really good graphics algorithms are simple. You are welcome to use the simplest algorithm. Sometimes that is the best one as well, because things have to be fast in graphics. But we are aiming for clarity to start here. Okay, so possible solution for your lab. What's being released today is you'll have 3 triangles like this. I've written some text over it. You can color them different things, as the requirements say. And lay them out in whatever order you want, but you'll have something like this in a image file for us. Okay, so with that, don't forget to do your in-class activity, and that's all for this lecture here. And we'll talk to you folks soon in office hours, and of course in the next live lesson. So hopefully this was a fun one, and you're excited to work on the software rasterizing stuff and do a little bit of programming here. It's going to be a lot of fun here. All right, we'll see you soon, folks.